Now that we're done with our discussion of forces, we want to turn our attention to the issue of centripetal acceleration. Okay, so centripetal acceleration. We find this idea of centripetal acceleration in systems where an object is moving in circular motion, or at least in some sort of curve. For our purposes, we'll consider almost uniformly circular motion. So this is the idea of things moving in circles. Okay, so let's just assume that we have an object, okay, and it can be a tennis ball attached to a rope, say, and if you attach a tennis ball to a rope, and I might need to make my rope just a little bit smaller. Give me just a second here. And if you attach a tennis ball to a rope and you swing that rope around, then it's going to trace out a circle. And that's no surprise. But the issue with centripetal acceleration is the ball doesn't have to change speed, okay? Okay, the ball does not have to change speed for centripetal acceleration to occur. So before we go any further with this, let's remind ourselves of the definition of acceleration. A change in the velocity of an object. Okay, so acceleration is a change in the velocity of an object, where velocity is the speed and direction of an object. So if either one of these change, if the speed changes or if the direction changes, okay, if either one of those change, then you have an acceleration. So now we go back to our tennis ball, and let's assume that the speed is constant, okay? Now I'm going to designate the speed with the letter V, all right? So don't get confused with V and velocity and S for speed, okay? I'm going to designate the speed as V, and you'll see why here in just a few moments. But let's assume that in this case it's constant, okay? So the actual speed of the ball isn't changing. Now, what direction is the ball pointing? Well, if it's at this point on the path, or on the circle, then the speed is going to be tangent to the circle. In other words, the speed is going to point straight up, like this. And we'll designate that as V initial. And if a few instances later the ball is then here, the speed is then going to be tangent and it's going to point in that direction. We'll call that V final. Okay, so I have one vector pointing up and I have another vector pointing off to the side. And one thing that I can do with vectors, okay, is I can move them around. As long as I don't change the direction they're pointing and the length that they have, then I can move them around with impunity. So I'm just going to kind of move over to the side here, and we'll redraw our initial vector here, VI, and our second vector, VF, and I'll put the origin right here. So this is VF, and they're not pointing in the same direction anymore. And in fact, VF is probably not quite right. VF is going to be more like this. Something like that. That's probably closer to the actual direction. So we have these two different directions, and So there's a change in direction, and we denote that change with this vector here, delta v. Now that's not terribly important. The whole point of this story is that the direction is indeed changing, right? It went from here at one instant, and then a couple instants later it's over here, and then a few instances later it'll be over here, and the speed is constantly going to be changing its direction, right? So the speed itself doesn't have to be changing, but the direction is. And so as long as one or the other, the speed or the direction, is changing, then we have an acceleration. So how do we actually describe what this acceleration is mathematically? So the idea is, okay, and this shouldn't be too hard to believe, that the faster the speed, the more quickly the velocity changes direction, and also the smaller the circle, the more quickly the velocity changes direction. This leads to a couple of mathematical ideas. First, that the centripetal acceleration will denote it as a cent for centripetal, okay, is going to be proportional, and I should actually use proportional sign, not an equal sign. Okay, it's going to be proportional to the velocity or the speed. We can say the speed in this case, all right? So the centripetal acceleration is going to be proportional to the speed, and in fact, okay, it's not quite evident from just this statement here, the faster the speed, the more quickly the velocity changes, or the direction changes. What actually occurs here is that this actually goes as the square of the speed, okay? We won't go through the mathematical analysis to show that, but this statement still agrees with this statement, right? That the faster the speed, the more quickly the velocity changes direction, or the higher the acceleration. So the faster the speed, well, the speed's always positive, so the square of that's always going to be positive. So the larger this number is, the larger the centripetal acceleration will be as well. Okay, so it's actually proportional to the square of the speed. But the centripetal acceleration is inversely proportional to the radius. Okay, the larger I make this radius, as r gets larger, then a gets smaller. And vice versa, as r gets smaller, a gets larger. Okay, and that shouldn't be too hard to understand, and that's simply what this statement here is saying, right? The smaller the radius, or the smaller the circle, equivalently the same thing, the more quickly the velocity changes direction. If I have a really, really small circle, it's changing direction very, very rapidly. So we can wrap both of these statements up into an equation, and we can say that the centripetal acceleration is equal to the square of the speed divided by the radius of the circle. So one might naturally ask, in the case of a tennis ball being swung around with a rope, right, what is supplying the acceleration? Okay, what is supplying the acceleration? Well, It turns out that if you analyze the situation very carefully, the ball, the direction of its motion, and in fact the magnitude of its motion, everything about the motion of the ball is directly related to the string or rope or whatever the case may be. Okay, the acceleration is directly related to the string, and in fact, because we've now defined this idea of centripetal acceleration, we can now define the idea of centripetal force, because remember, force is F equals ma. So we just replace this generic acceleration with the specific centripetal acceleration. And so F is going to be equal to the mass of the object experiencing the force times the centripetal acceleration it's experiencing, which is v squared over r. So the centripetal acceleration is directly related to the string, but in fact the string is actually giving, or supplying, if you will, a centripetal force. Okay, F cent. Okay, centripetal force. Now the force that is actually causing this is called tension. Okay, and tension is a force exerted by string, rope, chain, and objects of those ilk. Okay, so when we have something connecting two objects, in this case your hand and the ball, via a string or a rope or a rubber band or something like that. Okay, the generic term that we use for that force is called tension. Okay, so in fact, in this case, it's the tension in the string that is supplying the centripetal force, and hence the centripetal acceleration. Okay, so it's the tension in the string. So here's a question. If this is the sun, and this is the Earth's orbit around the sun. Now our orbit is not perfectly circular, but it's darn close. And so if this is the Earth, there's no literal string, right? There's no literal string attaching us to the sun. So what is supplying F cent, or the centripetal force, for Earth? I'll let you chew on that for a few minutes, and then we'll talk about that in the next video here. But what I want to do now is just one example using centripetal acceleration, and then talk about something like the merry-go-round, okay? And how things happen on the merry-go-round. And the merry-go-round you can actually extrapolate to other types of circular systems, be it a loop-de-loop in a airplane, or loops on amusement park rides, and so on and so forth. So we'll do that, but first let's do one example using centripetal acceleration. Okay, so let's assume that we have a ball, and let's say that it's swinging on a rope or on a string, and for our purposes, let's just consider the string to be completely horizontal. Okay, so it's just moving in a complete horizontal circle, and let's let the speed of the ball be 5 meters per second, and let's let the radius of the string, or the length of the string, which will turn out to be the radius of the circle, to be 0.5 meters, or 50 centimeters. Okay, so what is the centripetal acceleration? Okay, well, to do this, all we need to do is plug the values into our formula here. So we're going to get 5 meters per second quantity squared divided by 0.5 meters. And what does this turn into? Well, this is of course going to be 25. Now 25 divided by 5 would be 5, but 25 divided by 0.5 is actually going to be 50. And what are our units? Okay, so we're going to get meters squared per second squared from our units here being squared, and then we divide that by meters. And so we have meters up top on our top fraction, and you can consider this as meters over 1. So we have a fraction divided by a fraction. Our meters squared are up top, and our meters here are up top, and we're just left with meters over seconds squared, which is in fact the units of acceleration. So we're good. Okay, so the centripetal acceleration of this object is going to be 50 meters per second squared. If we knew the mass, and for just kicks and giggles, we can say that the mass is 0.25 kilograms. Okay, so then what's the centripetal force? Well, the centripetal force is just equal to m times AC, which is going to be 0.25, not 0.5, but 0.25 kilograms times 50 meters per second squared, and that turns out to be 12.5 newtons. Okay, so the tension in the rope, if I'd asked you what is the tension in the rope, that is the same thing as asking what is the centripetal force, because remember, it's the rope that is supplying that force. So the centripetal force experienced by the ball, or equivalently, the centripetal force being supplied by the rope, is going to be this 12.5 newtons. Okay? Okay, so now let's talk about the Ferris wheel. Okay, so this is a discussion that your book has, but I wanted to make sure that we went over it so that things were clear. All right, so let's assume you have a Ferris wheel here, and it's locked into the ground and sturdy, and let's say that it's moving this way. All right, now there are some peculiar things that happen with the Ferris wheel, because now we're not just interested in the centripetal forces acting on the rider, but we're also concerned with the weight of the rider and the normal force that the seat is supplying. So remember, okay, one thing actually that I haven't mentioned yet that I really should mention, if we go back to the Earth or the tennis ball, it doesn't really matter which. Okay, in both cases, the tennis ball being swung around on the string, or the Earth in orbit around the Sun, in both cases, what direction is the centripetal force acting? Okay, in what direction is the centripetal force acting? Well, in the case of the Earth and the Sun, it might not be too hard to imagine that even though at any given instant we're moving this way, the force that's actually keeping us in orbit is actually pointed directly toward the Sun. Okay, so the force is actually pointed toward the center. And the same thing with the tension in the ball. If the string were to suddenly snap, right, then the ball would fly off in this direction, and that means that it's the string supplying the force, meaning that the force is pointing toward the center of the circle. So centripetal forces always point toward center of the circle. Okay? Centripetal forces always point toward the center of the circle. And so, with the Ferris wheel here, wherever you are on the wheel, your overall centripetal force is going to be pointed toward the center. Okay? Now, there are 4 specific points that are of particular interest to the Ferris wheel. Okay? And these points are at the top, the bottom, and the 2 sides. Now, the reason being will probably become clear here in a minute, but let me just explain. So imagine that you're on one of the sides and you are sitting in your seat, and at this point, what forces are acting on you? Okay? What forces are acting on you? Well, you actually have only 2 forces acting on you at this particular point. Okay? You have the gravitational force acting down, which is your weight, your mass times gravity, and the normal force of the seat is pushing you up. Okay? Now, at this point, what direction are you accelerating? Okay? At this point, in what direction are you accelerating? Well, the only acceleration you're feeling is centripetal acceleration, which must be toward the center. So that means at the sides, because you're not falling or rising due to either your weight or the normal force, then at the sides, your weight must equal your normal force. Now, what about the bottom? Okay? What about the bottom? So if we have our cart here and our person here, what's going on here? So again, your weight is going to be acting downward, and the normal force will be pushing you upward. But in this case, the centripetal acceleration, or the centripetal force, is also pointing upward. Now, when you're on a ride like this, like a Ferris wheel, the centripetal force is your net force. Okay? So the centripetal force is going to be a result of the sum of all your other forces. Well, what forces are acting on you at this particular point? Okay? What forces are acting on you at this particular point? Well, we have the normal force acting up and we have the weight acting down. And if we let up be the positive direction, then the F net is also positive. And so we can say that F net is equal to the normal force minus the weight. Now, something peculiar happens at the bottom of the Ferris wheel or a roller coaster. If you go over a hill and then you come to the bottom of a hill, you feel heavy. This is also akin to the elevator when it starts to immediately move up and you feel immediately slightly heavier until it starts moving at a constant velocity. But your apparent weight, or how heavy you feel, is directly related to the normal force. Okay? So if we look at this equation and we solve for the normal force, we see that your apparent weight, or how heavy you feel, is equal to your weight plus the centripetal acceleration, or the centripetal force. Okay, so that's why you feel heavier at the bottom. At the top, okay, at the top, whoops, if we have our cart, then we'll have our normal force upward and our weight downward, as well as the centripetal force downward. Okay? So in this case, because up is positive, down is negative, we can write F equals ma as negative F net equals the normal force minus the weight. Now, if we solve for the normal force in this case, the normal force is going to equal our weight minus the centripetal force. Okay? So we actually feel light. You feel lighter at the top of a hill, and you feel heavy at the bottom of a hill. Okay, so I wanted to make that explicitly clear to you. In the next video, we'll actually start to talk about gravity, and we'll answer the question of what keeps the Earth going around the Sun, what is actually supplying the centripetal acceleration there. And we will see you next time.